Hello everyone, welcome back to our course on abstract algebra. Today we're going to be talking about the isomorphism theorems. The isomorphism theorems are some very important theorems that actually appear in several different shapes in abstract algebra because the theorems were originally formulated for modules, and they hold for modules, they also hold for ranks, they also hold for groups. And here we're only going to see them in terms of group theory, but later if you keep studying abstract algebra, then you will see them for rings and so on. Now, as I said, they were introduced by Emmy Noether, a German mathematician who is one of the most important figures in all of mathematics, and in fact, in physics also. Some of the theorems by Noether are incredibly useful in physics. And Emmy Noether was extremely influential in how we discuss and we treat algebra today because of the formulation of the isomorphism theorems. The way we present and we talk about abstract algebra is very much due to her work, and in particular her paper of 1927 where these theorems were introduced. So let's go ahead and start with the theorems. There are three isomorphism theorems, and then there is an extra one that we'll talk about in the next video, the correspondence theorem. But the first isomorphism theorem we've already seen in the previous video through some examples, and it's about kernels of homomorphisms. So let's state that. Let psi from G to H be a group homomorphism, and let K be the kernel of psi. Remember that we saw in the video about homomorphisms that the kernels of group homomorphisms are normal groups. So we can do a quotient, and what happens is that G quotient K, K is normal, so G over K is a group, is isomorphic to the image of psi via the isomorphism induced by the hom that goes from GK to the image that sends a coset GK to the image of the representative. Okay, so it's going to give us an isomorphism, and in fact, it tells you exactly what the isomorphism is. Now, there are several things to check. First of all, we're going to have to check that this is well defined. We are defining this isomorphism on classes, on cosets, by the value on one representative. So the very first thing to do is to check that this is well defined. So let's do so. So here's the proof of the first isomorphism theorem. And without loss of generality, I'm going to assume that psi is surjective. Otherwise, we replace H by the image of psi, and then it would be surjective. So I'm going to just assume that it's surjective, so I don't have to keep writing psi of G. And the very first thing to check is that we define psi bar from GK to psi of G, so now it's just H, such that K is the kernel of psi, and this was defined by GK going to psi of G. And so we want to check that this is well defined, and it's well defined. How are we going to do so? Well, suppose that I have two representatives for the same coset. Then I want to know that, so we want to show that psi bar of GK is the same as psi bar of G prime K. But if this is true, then G prime is in the coset GK. So G prime is G times little k for some k in K. And therefore, let's see, how much is psi of G prime K? G prime K evaluated via psi bar is just psi of G prime. Psi of G prime is psi of GK. And because psi is a group Hom, this is psi of G times psi of little k. And now k is in the kernel. So psi of G times psi of k is in the kernel. So it's just the identity in H, which is then just psi of G, but that is the image through psi bar of the coset GK. And therefore, we are done. We get the same value regardless of the generator of or the representative of my coset that I'm using to define the map. So it is well defined. Great. Let's now prove that psi bar is a group homomorphism, and then it is in fact an isomorphism. So I need to prove that it's bijective. So let's prove first that psi is surjective. Let's see, why is that true? Well, let H be in H. I want to show that there is something in the quotient group that maps to H. So that H, since it is surjective, this is psi of G, and therefore there is something in G that maps to H, and therefore, how much is psi bar of that coset generated by G? That is psi of G, which is H, and so psi bar is surjective, just like psi was. Okay, so that's done. Now I want to show that psi bar is injective, to show that it is in fact bijective. So now suppose that I have psi bar of GK gives me the same as psi bar of some other coset, G prime K, for some G and G prime in G. And I want to show that those are actually the same coset. Okay, this is by definition psi of G, and this is by definition psi of G prime. And these are the same. So psi G is equal to psi of G prime. That implies if I multiply on the left by the multiplicative inverse of this element, that tells me that psi G prime inverse psi of G is the identity in H. And now by the properties of homomorphisms, the inverse of a psi value is psi of the inverse. So this is the same as psi of G prime inverse psi of G, which is by the group Hom properties, this is psi of G prime inverse G. Okay, so what that tells me is that this element went to the kernel, and therefore it tells me that G prime inverse G is in the kernel, but that means that that G prime, that in fact by the we can write it as G prime inverse G is some little k in K, and therefore G itself is G prime K. So that belongs to G prime K. But when we have that one generator of a coset is in the other coset, then the cosets are the same, because we prove that cosets are either exactly the same or disjoint or completely disjoint. So what that says is that GK, the cosets are exactly the same, and therefore psi bar is injective, which is what I wanted to check. Okay, so that shows that psi is a bijection. And therefore, we only need to prove that psi bar respects group structure. So let's do that now. Let's prove that psi respects group structure. So what I need to show now is that suppose I have let G and G prime be arbitrary, then how much is psi of a coset times a coset? That by definition of the product on the quotient group, the way we multiply cosets is just G prime, K. I don't need to start here really. That's that coset. Now, by the definition of psi bar, this is just psi evaluated at the generator of the coset. Psi itself is a group homomorphism, so it does respect structure. So this is psi of G prime, and psi of G is the value through psi bar of the coset GK, and psi of G prime is the value through psi bar of the coset G prime K. And therefore, it does respect group structure, and therefore psi bar is a group isomorphism, which is what I wanted to prove, and it is the end of the proof of the first isomorphism theorem. Let's see some examples that we've already worked out actually in the previous video, but let's see that the isomorphism theorem tells me exactly what that isomorphism is between the quotient and the image. So the first one, remember that we had the sign from Sn to plus minus 1 that sends sigma to 1 if sigma can be expressed as a product of an even number of transpositions, and minus 1 if sigma is odd, i.e. if sigma can be expressed as a product of an odd number of transpositions. This is a Hom, and it is in fact surjective. So the first isomorphism theorem tells me that S and the kernel, by the way, so it is a Hom, and the kernel is the alternating group. So the first isomorphism theorem tells me that Sn modulo An is isomorphic to plus minus 1, which is just Z modulo 2, in turn isomorphic to Z modulo 2, via the map that sends any coset to the sign of the generator. So that is a isomorphism. It is an isomorphism, and it's an isomorphism because it's precisely what the first isomorphism theorem tells you, that that map in particular has to be an isomorphism. Similarly, we also saw that the determinant map from GL2R down to R cross is a surjective Hom. The kernel is SL2 over the real numbers, and therefore the first isomorphism theorem tells me that GL2R modulo SL2R is isomorphic to the non-zero reals under multiplication via the map that sends a coset to the determinant of the the determinant of the matrix that represents that coset. So that is an isomorphism, and it's the isomorphism that is provided by the first isomorphism theorem. Now we turn to the second isomorphism theorem. The second isomorphism theorem, it also has to do with a quotient, and it has to do with the following quotient. Let H be a subgroup, and let N be another subgroup of G, which is normal, be a normal subgroup. Then, first of all, H intersect N is normal in H. Okay, that is not difficult to prove. And then what it does bring up, though, is that then what is H quotient by H intersect N? How do I recognize that in terms of G? Well, what happens is that, well, first of all, Hn, the subset that is elements of H times elements of N, it turns out that this is a subgroup of G, and the actual isomorphism is that it tells me what this is isomorphic to. H modulo H intersect N is isomorphic to Hn modulo N, which is in turn a subgroup of G modulo N. So it gives me an isomorphism type for the quotient of H modulo H intersect N. I'm not going to prove this theorem, but I want to give you an idea of how to use it. So I'm going to give you an example. So let's prove or give you an example as follows. Let G be GL2 R, 2 by 2 real matrices with non-zero determinant. H is going to be SL2 R. These are 2 by 2 matrices, determinant 1. And but for a normal subgroup, I'm going to pick R star times the identity. So these are matrices A0, 0, A for any A in the non-zero reals. It turns out that N is normal in G, and then what is the intersection of H and N? So that is SL2, 2 by 2 matrices, determinant 1, intersect with matrices that are multiples of the identity. The only matrices that are multiple of the identity and the determinant is 1. Notice that the determinant here is A squared. So to have determinant 1, it has to be that A is plus or minus 1. So it is precisely plus or minus 1, 0, 0, plus or minus 1. There's only 2 matrices in there. So what is SL2 R quotient by plus minus 1 plus minus 1? So this is just the identity and minus identity. This quotient by the second isomorphism theorem will be the product. By the way, how much is H times N? H times N is, well, it's all of SL2 times matrices that have any determinant, really. So H times N is actually all of G. So this is isomorphic to H times N modulo N, which is all of G modulo N, which is in fact all of GL2 R modulo the subgroup N, which were just every multiple of the identity. So it gives me an isomorphism between this and this other group. Okay. So now let's look at the third isomorphism theorem. The third isomorphism theorem is also a theorem about quotients. So really these theorems should be called the quotient theorems. But in any case, this is what it says. Let G be a group, and let we're going to have a group N inside a subgroup H inside G. So all of these are subgroups such that N is normal in G and H is normal in G. Then two things happen. One is that H modulo N is normal in G modulo N. And then the question is, okay, well, then what is that quotient, G modulo N, modulo H modulo N? And it turns out that there is this sort of cancellation of n's, and this is isomorphic to G modulo H. Of course, this is a quotient group. This is a quotient group, so it's not like I can cancel those n's and just get this group. But that is what ends up happening. And so sometimes it is called the cancellation theorem because it resembles what happens with fractions. That if I have two fractions, two rational numbers like this, then this is going to be just a divided by b. So it looks like that, but it's not exactly that what's happening. But in any case, we can prove an isomorphism of this type. I am not going to prove this theorem. You can find the proof in most books on algebra, but I do want to give you an example of how to use the theorem or how the theorem actually works. So what I'm going to take for my G is actually just the integers, and then I'm going to take for H subgroup, which is 4 times the integers, and then n is going to be 12 times the integers. So the multiples of 12 are in particular multiples of 4, and the multiples of 4 are integers. So there is an inclusion like that. And we do have that 12 is normal. Every subgroup of an abelian group is normal. So these are normal subgroups of the integers. So I can do quotients. I can look at z modulo 12z and do the quotient by 4z modulo 12z and try to figure out what is happening here in this quotient and what is this going to be isomorphic to. And what the theorem tells me is that, by the way, let me just rewrite this. So these are the classes 0, 1, up to 11 modulo 12. And this is the subgroup. It corresponds to the subgroup of multiples of 4 in here. So these are the classes of 0, 4, and 8 modulo 12. And what the theorem tells you is that this has to be isomorphic to sort of canceling the 12s. And this is going to be just isomorphic to z modulo 4z. Now notice that this is a cyclic group, so the quotient will be cyclic. What is the size of this group? The size of this group will be the size of the top, 12 divided by the size of the bottom, which is 3. So it's a group of size 4. It's cyclic, and we know that every cyclic group of size 4 is isomorphic to z modulo 4. But now the fact is that the third isomorphism theorem already told us right away that that would be the isomorphism class of this quotient of quotients. Okay, so I'm going to stop here, and then next time what I'm going to prove is one more isomorphism theorem, or a theorem that's usually proved along these isomorphism theorems, that is called the correspondence theorem, that is going to classify what are the subgroups in a quotient group.